Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Strain Gauge Factor and Temperature Transducers from the paper Electronics. After completing this module, you will be able to learn the following. First, we will derive the strain gauge factor. That is, the expression of the gauge factor will be discussed. Second, we will discuss about the temperature transducers, that is its working principle. Third, the different types of temperature transducers like RTD, platinum resistance thermometer, thermistor, they will be discussed in detail. Lastly, the principle of measurement of RTD, platinum resistance thermometer, thermistor will be discussed and their advantages and disadvantages. So students, let us start with the basic introduction about the module. While there are several methods of measuring the strain, the most common is with a strain gauge, which is a device whose electrical resistance varies in proportion to the amount of strain in the device. For example, the piezoresistive strain gauge is a semiconductor device whose resistance varies non-linearly with the strain. The most widely used gauge, however, it is bonded metallic strain gauge. So the metallic strain gauge consists of very fine wire, or more commonly the metallic foil, arranged in a grid pattern. So strain gauges, they are available commercially with nominal resistances values from 30 to 3000 ohms, with 120, 350 and 1000 ohms being the most common values. So a fundamental parameter of the strain gauge is the sensitivity to the strain, which is expressed quantitatively by the gauge factor GF. Ideally, we would like the resistance of the strain gauge to change only in response to the applied strain. However, strain gauge material as well as the specimen material to which the gauge is applied will also respond to the changes in the temperature. So the strain gauge manufacturers attempt to minimize the sensitivity to the temperature by processing the gauge material to compensate for the thermal expansion of the specimen material for which the gauge is intended, while compensated gauges reduce the thermal sensitivity. They do not totally remove it. So the temperature transducers, the next part of this module, they are vital to a variety of everyday products. For example, the household ovens, refrigerators and thermostats all rely on temperature maintenance and control in order to function properly. Temperature control also has applications in chemical engineering. Examples of this include maintaining the temperature of a chemical reactor at the set point, the ideal set point, monitoring the temperature of a possible runaway reaction to ensure the safety of the employees, and maintaining the temperature of streams released to the environment to minimize the harmful environmental impact. So while temperature is generally sensed by humans as hot, neutral or cold, chemical engineering requires precise quantitative measurements of temperature in order to accurately control a process. This is achieved through the use of temperature transducers and regulators, which process the signal they receive from the sensors. Strain gauge factor. So the resistance is related to the length of the wire as R equal to rho L by A, where rho is the specific resistance of the material in ohm meter. And here L is the length of the conductor in meters and A is the area of the conductor in meter square. So students, there are two important parameters and these are the change in the gauge resistance and the second one is the change in the length. So gauge factor is nothing but the measurement of the sensitivity of the material to the strain. So we can define the gauge factor GF as the ratio of the change in the resistance delta R by R to the change in the length delta L by L. That is GF or K is equal to delta R by R divided by delta L by L, where K is the gauge factor, delta R is the change in the resistance in ohm, R is the initial resistance without any strain, delta L is the change in the length in meters, and L is the length in meter without any strain. So strain is defined as the change in the length divided by the original length. That is sigma equal to delta L by L, which implies that K is equal to delta R by R divided by sigma. So students, let us now discuss the derivation for the strain gauge. The resistance of the conductor of uniform cross section is given by R equal to rho multiplied by length by area. So R will be given by rho L by pi R square. Since R, that is the radius, equal to d by 2, where d is the diameter, therefore R square is equal to d square by 4. Now putting the value of R square in capital R, we have R is equal to rho L by pi d square by 4. So when the conductor is stressed due to the strain, the length of the conductor increases by delta L and the simultaneously decreases by delta D in its diameter. Hence the resistance can now be written as Rs equal to rho multiplied by L plus delta L divided by pi by 4 multiplied by D minus delta D the whole square, which is equal to, that is expanding D minus delta D the whole square equal to rho multiplied by L plus delta L divided by pi by 4 multiplied by d square minus 2d delta d plus delta d square. Since delta d is small and delta d square can be neglected, so we can write Rs equal to rho multiplied by L plus delta L divided by pi by 4 multiplied by d square minus 2d delta d, which is equal to rho L multiplied by 1 plus delta L by L divided by pi by 4 d square 1 minus 2 delta d by d. So we mark this equation as 1. Now Poisson's ratio mu is defined as the ratio of the strain in the lateral direction to the strain in the axial direction. That is, mu is equal to delta d by d, divided by delta L by L. Therefore, delta D by D will be equal to mu delta L by L. So substituting for delta D by D in equation 1, which was previously discussed, we get Rs equal to rho L multiplied by 1 plus delta L by L divided by pi by 4 d square multiplied by 1 minus 2 mu delta L by L. So rationalizing above equation, we get Rs equal to rho L multiplied by 1 plus delta L by L divided by pi by 4 d square multiplied by 1 minus 2 mu delta L by L. This is multiplied by 1 plus 2 mu delta L by L divided by 1 plus 2 mu delta L by L. So we get Rs equal to rho L multiplied by 1 plus 2 mu delta L by L plus delta L by L plus 2 mu delta L square by L square divided by pi by 4 d square multiplied by 1 minus 4 mu square delta L square by L square. So students, since delta L is very small, so we can neglect the higher powers of delta L in the previous equation, and we can write the expression for Rs as rho L multiplied by 1 plus 2 mu delta L by L plus delta L by L divided by pi by 4 d square multiplied by Rs. This is equal to rho L multiplied by 1 plus 2 mu plus 1 multiplied by delta L by L divided by pi by 4 d square. So Rs will be equal to rho L by pi by 4 d square plus rho L multiplied by 2 mu plus 1 delta L by L divided by pi by 4 d square. Now R equal to rho L by pi d square by 4. Therefore, Rs will be equal to R plus delta R. So now comparing these two equations, we can write delta R is equal to rho L 2 mu plus 1 delta L by L divided by pi by 4 d square. So the gauge factor will be K is equal to delta R by R divided by delta L by L equal to delta L by L multiplied by 1 plus 2 mu divided by delta L by L. Therefore, K is equal to 1 plus 2 mu. This is how the gauge factor is related to the Poisson's ratio. Let us now discuss about the temperature transducers. They are the transducers which measures the temperature. Temperature is a measure of random motion of atoms or molecules within a gas, solid or liquid materials. So the greater the kinetic energy, the greater the temperature. Temperature can be measured in Celsius or Fahrenheit, relative scale, and Kelvin, that is the absolute scale. The most commonly used temperature sensor is the conventional mercury-based thermometer, and we have other different types of temperature transducers: resistance-based, thermocouple-based, semiconductor-based. Let us now discuss about the one of the temperature transducer, that is RTD. RTD is known as the resistance temperature detector. So RTDs are the temperature sensors that contains a resistor that changes resistance value as its temperature changes. So mostly RTD elements consist of a length of fine coiled wire wrapped around a ceramic or a glass core. So the element is usually fragile, so it is often placed inside a sheathed probe to protect it. So the RTD element is made from a pure material whose resistance at various temperatures has been documented. The material has a predictable change in the resistance as the temperature changes. It is this predictable change that is used to determine the temperature. So students, the relationship between the temperature and the resistance of conductors can be calculated from this equation as R equal to R naught 1 plus alpha delta T, where R is the resistance of the conductor at temperature T. R naught is the resistance at the reference temperature, usually 20 degrees Celsius. Alpha is the temperature coefficient of resistance, and delta T is the difference between the operating and the reference temperature. So students, this figure shows a typical RTD design where we have a coiled resistance element which is provided with a core and the connecting wires. Sensing element. The characteristic of the sensing element determines the sensitivity and operating temperature range of the instrument. So the smaller the sensing element, less heat is required to raise its temperature and faster is its response. For example, platinum, nickel, copper. Platinum is most commonly used because the resistivity tends to increase less rapidly at higher temperatures than the others, and thus its range is around 260 to 1100 degrees Celsius. So there are types of commonly used sensitive resistive elements are wire wound resistance, thermistor, PTC semiconductor resistance. So the characteristics of semi-sensing element are number 1, it exhibits relatively large resistance change in temperature. Number 2, the material used should be stable in its characteristics, that is, neither its resistance nor the temperature coefficient of resistance should undergo permanent change with time. Thirdly, there should be a linear change in resistance with a change in temperature. Platinum resistance thermometer. So this is the another type of temperature transducer where the changes in the resistance caused by the changes in the temperature are detected by Wheatstone bridge. The temperature sensing element, that is nickel, copper or platinum, they are contained in a bulb or a well along with the balancing bridge. They forms the essential component of a temperature measuring system. So the schematic of the platinum resistance thermometer is shown in this figure. Now consider RS, the resistance of the sensing element, which is made up of a material having a high temperature coefficient. R1, R2, R5, they are considered as the resistances that are practically constant under normal temperature changes. So students, when no current flows through the galvanometer, the normal principle of Wheatstone's bridge states that R1 by R2 equal to Rs by R5. In normal practice, the sensing element is away from the indicator and its leads have resistances R3 and R4. Therefore, R1 by R2 equal to Rs plus R3 plus R4 by R5. So now, as the resistance Rs changes, balance cannot be maintained and the galvanometer shows a deflection which can be calibrated to give a suitable temperature scale. Let us now discuss the advantages of resistance thermometer. The measurement is accurate, it has lot of flexibility with respect to the choice of measuring instrument. Indicators, controllers or recorders can also be operated. More than one resistive sensing element can be clubbed. It can be easily installed and replaced. Accuracy can be verified. Limits of errors are less. It has a stable performance. Size is also small. Whereas it comes with certain limitations, that is, it has a high cost, need of bridge circuit and power source, there is a possibility of self-heating, and it has a large size as compared to thermocouples. Let us now discuss about the thermistors, another type of temperature transducers, and they are thermally sensitive resistors. As a matter of fact, the resistance of all the resistors may vary with temperature. But thermistors, they are constructed of materials with a resistivity that is especially sensitive to only the temperature. That is, delta R is equal to alpha delta T, where delta R is the change in the resistance corresponding to the temperature change of delta T. And alpha is what? Alpha is the temperature coefficient of resistivity. So students, there are two categories of thermistors. First is a positive thermistor with positive temperature coefficient. Second one is a negative thermistor with a negative temperature coefficient. Resistors that are not thermistors, they have alpha equal to 0 so that the resistance remains nearly constant over a wide temperature range. Thermistors, they are made from certain metal oxides, manganese, cobalt, uranium, etc., whose resistance decreases with increase in temperature. Because the resistance characteristics falls off with increasing temperature, they are called as negative temperature coefficient NTC sensors. So due to the nature of a basic process, the number of conducting electrons they increases exponentially with temperature. The characteristics therefore exhibits a strong rising form. This pronounced non-linearity is the disadvantage over RTDs. In some cases, the resistance decreases by 5% for each 1 degree Celsius rise in temperature, making it more sensitive and hence useful for precision temperature measurement. So depending on the compositions, the resistivity may have its value anywhere from 10 to the power minus 1 to 10 to the power 9 ohm centimeter. So the resistance value of thermistors at 20 degrees Celsius may lie in the range of 100 ohms to 1 mega ohms. Material is brittle and hence the element in the wire form cannot be obtained. So this figure shows the variation of a log of resistance, that is in ohms, versus the temperature, and it shows a decreasing trend. And here the elements are in the form of beads, rods, and discs of different sizes. The advantages of thermistor: number one, they have a very small size and low cost, fast response over narrow temperature range, good sensitivity in the negative temperature coefficient NTC region. They have a cold junction compensation, which is not required in this case due to the dependence of resistance on absolute temperature. Contact and lead resistance problems are not encountered due to large resistance. Now, thermistors come with certain disadvantages also. Number one, they have non-linearity in resistance versus temperature characteristics. Secondly, unsuitable for wide temperature range. Third, they have very low excitation current to avoid the self-heating. The next one is the need of shielded power lines, filters, etc. due to high resistance. So students, let us now summarize what we have learnt in this module. First, we derive the expression of the strain gauge factor, which is a very important parameter for the performance of strain gauges. Secondly, we discussed about the temperature transducers, that is its principle of working. Thirdly, we discussed the various types of temperature transducers like RTD, platinum resistance thermometer, and thermistor. Lastly, the principle of measurement of RTD, platinum resistance thermometer, and thermistors, it was discussed in detail, and their advantages and disadvantages. Thank you.